Continuing our set on the CCEA A2 Physics 2011 paper, Unit 2 Fields and Their Applications, and question 7 is about particle accelerators. A synchrotron is a type of particle accelerator in which the kinetic energy of charged particle is progressively increased as the particle moves around a circular track. Figure 7.1 shows the main components in this type of particle accelerator. And you can see what we've got here. We've got a linac feeding into the circle. And then we've got two types of thing. These dipole magnets placed at various positions. And then these 4 positions of electrodes connected to a high frequency alternating voltage. And the pipe is also in a vacuum. So, A1, explain why there must be a vacuum in the beam pipe. And obviously, we're trying to accelerate these particles, and if this beam, as it went round, if the beam was constantly colliding with gas atoms because of the presence of a gas in the beam tube, then we would have to be supplying more and more energy. It could lead to lots of different problems, but the main one would be that the beam wouldn't continue to hold its energy. We'd have to keep accelerating it to overcome the losses as it collided with gas atoms. So we would say something along those lines. Gas atoms present in the beam tube will be struck by the beam, causing the beam to lose energy. Part 2 then, state the function of the electrodes connected to the high frequency alternating voltage. So these are the accelerating pushes that we get at these various points. They're the ones that are adding energy to the particles by giving them a little push as they go round. So, something along those lines. These provide the accelerating pushes that cause the protons to gain energy. Part 3. Protons are introduced to a synchrotron of diameter 12 kilometers from a linear accelerator. The synchrotron increases the energy of the protons until they are moving at 98% of the speed of light. However, when moving at this speed, the protons have an effective mass that is 5 times larger than that given in the datasheet. Calculate the required magnetic flux density of the dipole magnets needed at this proton speed. So, in this kind of question, we have that the magnetic force is providing the centripetal force. So BQV is equal to mv squared over r. So we're after the B value here, so we need B on its own. And we say that B is equal to mv squared over r q v. And so we're going to get some cancelling with these V's. And that simplifies then to mv over r q. So substituting into that, we get B equal to, well, it's going to be 5 times the normal mass of a proton, which is 1.67 times 10 to the minus 27. Sorry. That was even messier. Okay, so because we were told that it's 5 times the mass that it would normally be, and we're multiplying by 0.98 of the speed of light, and then we've r and q on the bottom line, and if the diameter is 12 kilometers, then r is going to be 6 times 10 to the 3, 6 kilometers for r, because it's half diameter is the radius, and multiplying by the charge, which is your standard elementary charge of 1.6 times 10 to the minus 19. Now we just need to feed that through the calculator to get the B value in Teslas. And I probably should have used a fraction mode. But to two significant figures, that's going to be 2.56 times 10 to the minus 3. Or sorry, three significant figures. 2.56 times 10 to the minus 3 of a Tesla. In the film Angels and Demons, 0.125 gram of antimatter is stolen from the particle accelerator complex at CERN. What is antimatter? And then part 2, calculate the energy that would be released in the annihilation of this quantity of antimatter. So the Mark scheme really just says that antimatter is matter that is composed of antiparticles, so we really tend to want to follow learning off answers that the Mark scheme says. You could say lots of different things for this, but I suppose if they're asking specifically for a particular response, then we should be learning off that response. Part 2 then, calculate the energy that would be released in the annihilation of this quantity. Well, this quantity, remember, is 0.125 grams. So let's say we had a little chunk of antimatter here, and we had a little chunk of matter. So we've got some matter, some antimatter, and we're going to throw those at each other and cause them to annihilate. So you've got 0.125 grams of each. So the important thing is to realize that in order to annihilate 0.125 grams of antimatter, you need just as much matter, and so it'll be 2 times that, the total amount of matter that gets annihilated. And then we just use Einstein's famous equation. Okay, so we're talking about 0.25 of a gram, which is 0.25 times 10 to the minus 3. Of a kilogram, and then we're multiplying that by c squared. And that gives us an energy of, so we get this value of 2.25 times 10 to the 13 joules. And that's that. Thanks for watching.